The Messenger mission was conceived, was wrapped around 6 science questions that we hope to address. And those science questions have been with us since Mariner 10. They have to do with fundamental aspects of the composition, the makeup, the evolution of Mercury. But also they are questions that we think we can answer from an orbiting spacecraft, from measurements we can make from orbit. And they are questions that bear on the family of inner planets that includes Mercury and of course also includes our Earth. The first question is, how did the inner planets form? And in particular, what process contributed to their differences in composition? And how did we end up with one planet, mostly iron metal? Because we believe that all the planets formed at about the same time, about 4.5 billion years ago. And in the case of the inner planets, they formed by common processes. And yet the outcomes we know are very different. We live on a planet with a wonderful climate and water oceans. Venus is a planet with a massive CO2 atmosphere and a runaway greenhouse that leaves the temperatures extraordinarily hot. In fact, it's the hottest surface temperature of any of the planets, even hotter than Mercury. Mars had possibly benign climates early in its history, but now is a cold and largely arid desert. And Mercury, heavily cratered Mercury, ended up with this huge core, a core occupying more than 60% of the mass of the planet. And the question is why? And there are different ideas. And what's nice about the ideas is we can test them. We can test them from orbit because the different ideas predict different outcomes for the chemistry of Mercury's surface material that we can sense with geochemical remote sensing instruments, such as the ones we carry on Messenger, from repeated measurements in orbit around the planet. The second question that we want to address is the geological history of Mercury. In particular, is the geological history of the side we haven't seen, similar to the side we have. With higher resolution color images on a global basis, can we see features that are diagnostic of geological processes that Mariner 10 missed, like evidence for volcanic activity, volcanic flow fronts, volcanic vents? Are there features on the side we haven't seen that are different? Could the two hemispheres have had a somewhat different history? It's not an astonishing outcome when we remember the history of exploration of Mars and of the Moon, that opposite hemispheres can be quite different. The third question we want to address is why tiny Mercury has a global magnetic field. It could be by Earth-like processes, a dynamo in a fluid outer core. It could be a fossil magnetic field that's permanently frozen in from an earlier time, because we know that the crust of Mars and the Moon has patches of magnetized crust. What makes that hypothesis a little bit unlikely, but we can't rule it out, is that Mercury's field seems to be global in scale, and so it looks like a bar magnet at the center of the planet. It doesn't look like patches of magnetized crust. So the thinking is that there's some kind of dynamo going on in a fluid outer core of Mercury, whether it's Earth-like or some more exotic dynamo, we don't know. The fourth question we're going after is the nature of Mercury's core. We know just from mean density that Mercury must be mostly core, 60% by mass. We also know from recent Earth-based radar that there's some fluid outer core. We don't know how thick. But what we're after is a proper assay of the size of the core, and if we can chase also the question of how much of the core is molten and how much is solid. To answer that question, again, requires an orbiter. We need measurements of the planet's gravitational field. We need improvements in the determination of the spin axis direction and the response of the planet to solar torques in its 88-day orbit around the Sun. The fifth question we're going after are those polar deposits. Another unusual aspect of Mercury is that the spin axis is almost perpendicular to its orbital plane. Now what that means is that if you're at one of the poles and you're down in the floor of an impact crater, you're in permanent shadow. The sun never shines on the floors of the polar craters. Earth-based radar showed us that the floors of the polar craters are covered in material that reflects radar signals and depolarizes them in a manner that is well matched elsewhere in the solar system by water ice. The same kind of effects are seen at the poles of Mars and on the surfaces of the Galilean satellites. And a leading idea, therefore, is that the polar craters are so cold because they're in permanent shadow that they can trap volatile materials like water as solids for billions of years. There are competing ideas, however, for what that volatile material might be that would be trapped in such cold floors of craters. And we've got to test the idea that what's there is water ice or some other material. And we'll do that by doing geochemical remote sensing of the crater floor material. We'll do that by looking at signatures in the high latitude atmosphere of gases coming off those polar deposits, and we'll do that also by imaging and by testing with altimetry the idea that all of the places that show these radar deposits are in fact in permanent shadow and are deep enough to be so. Then the final question we're going after is the nature of Mercury's tenuous atmosphere. We know that the materials in Mercury's atmosphere cannot be there for the lifetime of the planet. They are lost by processes that are reasonably well understood on much shorter time scales. So there must be processes for renewing that atmosphere. And we also know something about the composition. Mariner 10 measured the presence of hydrogen and helium and oxygen, and Earth-based astronomers have discovered some additional species, particularly sodium, potassium, calcium. And those last three species are so abundant in the atmosphere they can't come from the solar wind. They must come from material at the surface of Mercury. So they're either telling us about Mercury's intrinsic material or about material that has been sent to the surface of Mercury as a result of impacts of asteroids and comets.